Okay, thanks so much to the organisers of the workshop for the opportunity to present. What I chose to talk about is obviously related to the general topic of the specific session, and hopefully will build quite nicely on what Chiara and Roberto have just talked about. In the prior I guess the preceding version instance of this workshop was the 2001 Pacific Forum, and in that I gave some specific sentiments about performing simulations and their validation against observations in a New Zealand context. And so for those that are interested, you can see it on the PEER YouTube page or at this link, and therefore purposefully I chose to deviate slightly from largely repeating some of the same sentiments and talk more about the use of simulations and how we should think about the use case in terms of validation and acceptance criteria and the development of simulated ground motion databases. So I'm coming at this presentation from someone who runs simulations, but also as a civil engineer who makes use of simulations for response history analysis and who advises structural and geotechnical engineers on how they can make use of such simulations as well. So I guess the motivating statement is something along the lines of, a potential user, are these simulations a valid representation of reality for me to use? And the responder, whether that responder is the person performing the simulations or someone else that has some knowledge, naturally is, as you may have guessed, going to respond along the lines of it depends. And it depends on a multitude of factors, how accurate the representation of reality needs to be, what is the use case, what region of the world are you in, and so on and so forth. So I hope to tease out the answer to that question in a few different dimensions. As a brief outline, just introduce some terminology and way to break down the problem by thinking of things in terms of seismic risk and how we can perform seismic risk calculations using simulated ground motions. And there are a few different ways that simulated ground motions can fit into the seismic risk calculation. A couple of them have been touched on already. Talking specifically about the use cases more generally, how that relates to validation and acceptance criteria, again, building on some of the sentiments from presenters that have already talked, particularly Chiara, Roberto, and Ricardo, and then considerations for how that relates to how we might develop databases of simulations. Okay, so as I mentioned, first framing this in terms of seismic risk. Since this is a PEER forum, it would almost be remiss to not have some terminology from the PEER framework formula come up. So here is some representation of calculating seismic risk as a function of performing what is essentially the seismic hazard analysis, probabilistic seismic hazard analysis, as well as seismic demand analysis. So in this expression, we have engineering demand parameters, or a vector of these, which either represents multiple demands in a single structure. So for example, floor drifts and accelerations over the height of the structure, and or could represent multiple structures located at different locations. So if we're looking at, for example, regional risk analysis of the San Francisco Bay Area, that would be demands at different locations of structures in the area. The vector of intensity measures, again reflecting multiple attributes, either of the ground motion at the site, response spectra at different periods, duration, RES intensity, etc., and or representing multiple site locations. So again, in the regional risk context, that could be spectral acceleration at all the different locations in the Bay Area. And so then we have summation over all possible ruptures, if we're doing PSHA, the rate at which those ruptures occur, and integration over the different levels of ground motion intensity as part of that calculation for risk. So in this particular formulation, I've used the engineering demand parameter to refer to risk, but obviously you could substitute that out and either think of it as damage given intensity or loss given intensity using the common PEER notation in that regard as well. Okay, so how does that, when we frame it that way, I think it's useful to mathematically describe it so that then we can see in that mathematical or modular context how simulations can fit into various different use cases. And so first, in a sort of very broad sense schematically, there's two general domains in which simulations can be used in assessing seismic risk. And so in this schematic on the upper left-hand corner, We've got multiple seismic sources. In the upper right-hand corner, we've got some schematic representation of a structural model for which we're going to apply ground motions. Down in the bottom, we've got some description of intensity measures. You can think of that loosely as representing the seismic hazard at the site. And so generally speaking, we have the use of ground motions and ground motion simulations in particular can either be in the bottom left for seismic hazard analysis, where we take the seismic sources in the region, we simulate ground motions for all of those different seismic sources, we perform the integration or discrete summation, and we come up with seismic hazard curves, uniform hazard spectra, and so on and so forth. And then on the right-hand side, where we have the seismic hazard already performed, and we want to select a subset or ensemble of ground motions in order to perform seismic hazard analysis. Now, clearly in the long term, if we compare ourselves with analogies in weather forecasting, the use of physics-based simulations for weather forecasting is ubiquitous now over empirical weather forecasts, and clearly in the long term, that's the way things might go. As Ricardo was saying, the degree to which we have a hybrid between physics-based simulations and machine learning approaches is yet to be seen, but obviously there is a general trend towards increasing use of physics in the calculation. However, we're obviously in this interim transition from a purely empirical observational based approach toward that long-term future. And so while we're in that transition region, we do have a range of different alternative use cases where, for example, in the left-hand side, we perform seismic hazard analysis in the conventional way using empirical ground motion models, but then we use simulated ground motion models to help supplement recorded ground motion databases for that purpose of response history analysis. So that's just one example of the different roles simulations can play without having to provide the entire pipeline of the seismic risk calculation. So what does that look like in terms of response history analysis, starting more on the right-hand side of that prior diagram? In the context of our seismic risk equation, basically these two parts we would get from PSHA using conventional empirical ground motion models and a seismic source model. But then when we come to estimate the seismic demand, we're going to do a nonlinear analysis using software like OpenSeas or other equivalent finite element models. Rather than just applying conventionally recorded ground motions, we could make use of simulated ground motions, either in full or in part to supplement those recorded ground motions. Broadly speaking, we could probably break that into two different types. The first one would be where we're focused largely on code-based ground motion selection, which in the overwhelming majority of seismic codes worldwide, the focus is largely on response spectra. And then more generally speaking, if we're doing ground motion selection for performance-based earthquake engineering, we'd focus on other non-response spectral measures, for example, duration, RES intensity, CAV, etc., that we know clearly affect structural and geotechnical response, particularly for large levels of nonlinearity and plasticity. When we look at the left-hand side of the prior schematic diagram, thinking about seismic hazard analysis, what we're saying here is really that estimation of the distribution of intensity given a rupture, we would substitute out the conventional use of empirical ground motion models and replace them with simulations, or we could take a sort of hybrid path where we're making use of simulations to help constrain empirical ground motion models. And that's obviously been a key theme over the past decade or so, where we know empirical ground motion models aren't adequately constrained from observational data alone. So why does the simulation use case matter? So I've sort of highlighted these two general aspects, either for hazard analysis or response history analysis / ground motion selection, and then a couple of variations within those. Well, it will influence some key questions like the degree to which we care about the input physics versus the output ground motions. And what I mean by that is, do we actually care about the underlying physics in the simulation, what physics is accounted for and what isn't? For example, in the prior session, the discussion about dynamic versus kinematic / pseudodynamic rupture generators, or do we mainly just care about the nature of the resulting waveforms? And said another way, if the waveforms are okay according to the metrics that we care about, do we care if they were generated from a process that has true or best representation of our understanding of the physics. This is obviously relevant, again, with what Ricardo was just mentioning when we talk about machine learning, that clearly that's not going to treat the physics in at least a vector calculus type of approach. It's going to have latent representations of physics, but not explicit. The next one would be with respect to uncertainty, so whether the simulations consider model or parameter uncertainty explicitly. Most of simulations will have some baseline level of uncertainty. For example, rupture generators typically have some stochastic component in the slip distribution, so there's always going to be a little bit of variability if you generate nominally similar ruptures because of that stochastic process. So what I'm really talking about here is a more broad effort to comprehensively treat uncertainty by making all parameters have probabilistic distributions rather than many parameters in these simulation methods having calibrated constants as we currently have. One that hasn't come up a lot but should be relatively obvious and is a key attribute of performing simulations is the site or region specific nature that they have. So whether the simulations represent the specific geographic site or region that the structure is to be used for, or whether we take simulations from general regions and consider that they could potentially occur at our site of interest. And then fourthly, the complexity of the structural model. So what ground motion features the numerical models of the structures considered are sensitive to. And the model here is important in that real structural behavior, real geotechnical behavior is quite complicated, but often our model representations of those are quite simple, such that many of the things that actually affect structural response in reality don't actually affect structural model response, and given the idealized nature of these models. So let's explore each of these aspects a little bit further with a slide. So on the first one of input physics versus output ground motions. So as I was saying, the key question, does the underlying physics in the simulation matter or just the resulting ground motion? And so the example that, for example, Chiara did a nice job of summarizing in an Italian demonstration context is where we use ground motion simulations for code-based ground motion selection. So here's one example in a California context where if we're given a target spectrum and we simply want to select simulated ground motions to match that target, we predominantly care about the properties of the resulting ground motion. So how well do the intensity measures of those simulations match, in this case, the target spectrum, and we don't really care that much about the underlying physics that gave rise to the ground motion because we're already, by defining the target spectrum, we're already setting the intensity. So let's say, as an example, if you had a simulation method that actually over-predicted ground motion intensity for a magnitude 7 rupture, that's not really going to matter much because we're not focused on the distribution of intensity measure. Given rupture, we're already specifying the target spectrum. And so in this particular application case, actually the use of simulations is already widespread, where we typically take large magnitude, small source to site distance ruptures, and we add those to existing recorded databases that are naturally sparse in that particular magnitude distance range to supplement those databases to help us. And again, Chiara in particular was providing a nice illustration of that from an Italian context. One thing I would point out is that when we do that, we are still thinking about things in an ergodic framing, meaning that those simulations have been sometimes performed with a 1D velocity model or performed with a 3D velocity model for other regions of the world, and we just make the assumption that that ground motion that's been recorded or simulated could occur at our site of interest, whereas in reality there's no guarantee or no actual calculation that's done to see if that's the case. So we are making use of simulations in this regard, but it does still sort of, shall we say, ergodic and not site-specific in nature. The second topic with respect to uncertainty, so do we need to represent the distribution of intensity given rupture comprehensively via multiple realizations, or actually does it not matter? For code-based ground motion selection, the example used in the last slide, no, for the reasons I mentioned, largely that we're just focused on how well each individual time series matches the target spectra. For scenario ruptures, for example, scenario simulations of the Hayward fault, it would depend. If we were just focused on a single sort of reference simulation for something like emergency planning, e.g. the Hayward scenario, then really we're just picking some best reference case, and we're not too worried about rigorous uncertainty treatment. In contrast, if we actually want to perform seismic risk calculations for future Hayward scenarios, then clearly it would be desirable to have a range of plausible ruptures, and therefore it would be important to have uncertainty. For seismic hazard analysis, making use of ground motion prediction with simulations, then the answer is yes, it's really essential, and I would say that's sort of the holy grail of where we need to get to with simulations, is not just doing a good job predicting mean/median ground motion amplitudes, but also representing the uncertainty appropriately as well. And then there's that interim use case where we use simulations to inform empirical ground motion models. And so as the common application of that is to constrain median model development in these empirical models, then that really isn't required to comprehensively treat uncertainties. But if we want to use simulations to explore uncertainties in empirical ground motion models, then obviously it would be required. On the third topic about site region-specific nature of the simulations, so the framing question, does it matter if the simulations are for the specific site of interest or not? And so here we have this general progression where simulations can be performed in a 1D context, for example, on the bottom left, using tools like the SCEC broadband platform, all the way through to a 3D context for the specific region of interest. Again, if we're dealing with ground motion selection, it's common to make use of simulations for other regions of the world, or for generic 1D velocity, 3D, quote unquote, 3D simulations that are performed with a 1D velocity model. So as I referred to before, that's generally consistent with how we use recorded ground motions from other places in the world as well in an ergodic context. However, clearly it would be desirable to, even if we don't believe in an absolute sense the distribution of intensities predicted from simulations, it would obviously be desirable to be able to go to a lookup web tool, enter your latitude, longitude, for example, in the San Francisco Bay Area, download, tens, hundreds of ground motions, thousands of ground motions that have been recorded at your site from many different sources, and then check the spectrum compatibility of those. And that would be one obvious interim pathway. For seismic hazard, clearly, I would argue that the use of simulations in seismic hazard analysis would need to be for the specific site of interest. Otherwise, how would it be better than using conventional empirical ground motion models? And then lastly, the aspect on complexity of structural models. So what ground motion intensity measures matter for the structural model that would be used? And again, emphasizing that it is very typical in engineering practice that even though the structural response of common multi-story commercial buildings is actually quite complicated, the models that are used in consulting practice often can be relatively simple, and therefore that does result in some desensitivity of the true features of the ground motion that matter. So if we have some sort of continuum shown schematically on the bottom, from single degree of freedom to multi-degree of freedom model, but relatively simple, all the way through to trying as best as we can to represent the full problem. Then we can think of a few different examples of simulated ground motion. So for example, firstly, regional risk using single degree of freedom building models, or empirical fragility functions that are just based on PGA or response spectra. Then clearly, when we're thinking about validation, we're largely thinking about response spectra. If we're focused on code-based design checking for new structures, research, for example, here by Chandramohan in 2016, has shown that in most cases for the levels of ground motion intensity that we're checking in design, because collapse is so unlikely for new structures, things like duration and cumulative measures of intensity don't actually matter as much as we might think they do. Whereas in the third bullet, for general performance-based earthquake engineering assessments, and particularly where we have vulnerable structures, non-ductile structures, etc., then these non-spectral acceleration measures become quite important, like duration and cumulative measures. The last thing that often doesn't get as much attention as it should, because usually in a research environment, we often deal with seismic response models in 2 dimensions, particularly structural engineering, as opposed to in commercial engineering practice, 3-dimensional models are much more common, is the adequacy of the tri-component nature of the simulated ground motion. So what is the phasing and relative amplitudes of those two horizontal components, as well as, to a lesser extent, the vertical component. And that's particularly challenging at high frequencies, particularly if we're using hybrid ground motion simulation methods where the so-called high frequency, or sometimes referred to as stochastic method, has no notion of coherency in the two different horizontal components. So how does all this fit into validation and acceptance criteria? Well, there are many validation approaches that have been proposed, so-called frameworks, shall we say. Obviously, as frameworks, they're really just ways of organizing our thinking on the topic, and I show a couple here that I sort of anticipated might be relevant or familiar to some people in the audience, and also represent some of the speakers. So on the bottom left, Chiara was largely talking about some work from their effort there, and Ricardo was talking about work from the Southern California effort, which is sort of loosely related to the first paper that you can see on the upper left, as well as the one on the bottom. One just to mention very briefly, both because it's something that I've been involved in, and also it's something that hasn't been touched on by some of the previous presenters, is that site-specific nature, or the spatial extent of the way we think about the simulations. And Chiara talked about the spatial element, but she was referring to sort of spatial correlation, coherency, those sort of things, where here I'm referring to, are the simulations performed for your specific site, or are they performed for just your general region of the world, or actually they're not even performed for your particular country? So obviously that has a strong influence on what we can make use of them for, and clearly there's a lot of value, and obviously one of the low-hanging fruit is simulations just performed for generic regions of the world, where we assume, just like when we use recorded ground motions for ground motion selection, that we can just add them to supplement the database to give us those events for large magnitude, small source to site distances. But really where we want to move towards is having simulated ground motions that are useful for seismic hazard analysis, as well as that easier application of response history analysis. And so then very briefly on the topic of acceptance criteria, I think the key framing question is, how can we start getting simulations used more? The more they get used, the more the feedback loop of iteration will help accelerate their actual scientific development. And so from that perspective, I take sort of a very engineering view of what are we doing at the moment, and how can simulations be demonstrably better than our alternative conventional approach. So is using a specific simulation, and importantly, we don't want to just think of, that simulation method equals wave propagation code. Obviously, it refers to the underlying rupture generator that's used and the underlying velocity models for the region. And arguably, some of the assumptions there are much harder than actually the wave propagation itself. Is using that method better than empirical ground motion models, if we're talking about the hazard context, and recorded ground motion models, if we're talking about a ground motion simulation context? So we want to assess this via multiple test metrics that allow comparison of the model performance of the simulation prediction as well as the conventional prediction. So Chiara had a nice summary of this already, so I'll just go through it very quickly. So we can compare with prediction residuals from historic events with empirical models at the site of interest, and generally sort of basic physical expectations when we extrapolate beyond data. And for ground motion selection, do we get the same distribution of seismic demand if we use simulated ground motions versus that we see with recorded ground motions? As a brief aside in acceptance criteria, I'd say that Ricardo had a couple of nice slides on scalar goodness of fit scores. I think those scores are really useful for comparing sort of in a general sense, how well does simulations match observations, and for comparing the performance of one or more simulations against observations, but they don't actually allow us to compare simulations with the conventional engineering way we solve the problem, which is empirical ground motion models or using recorded ground motions, and therefore they're not that well suited as acceptance criteria for should we use simulations or should we stick with the non-simulation sort of conventional approaches. So what does that mean, lastly, in terms of considerations for simulated databases? And here I want to emphasize that when I think of simulated ground motion databases, I'm thinking of the general problem of databases that federate simulations from different groups using different methods and or performed in different regions, as opposed to, for example, a database from a single set of simulations for a specific region simulation method individual group that largely can just be thought of as almost sort of supplementary material associated with a journal paper that describes that particular piece of work. That database may or may not have some sort of nice user interface, but I think the first bullet point here forces us to understand, how do we have that heterogeneous combination of many different simulation methods? Because, of course, unlike databases of observed ground motions, which are measurements of reality after we remove the bad, low-quality records, all simulations are model approximations, and that approximation accuracy is going to be a function of many features listed here, for example. If we try to have metadata attributes in a database that seek to classify all of these different features of the simulations and bin them into different groups, etc., I'd argue that will be at a minimum very onerous and more likely quite prohibitive, because obviously simulations are also advancing with time, and therefore an alternative might be simply to focus on whether specific simulations meet the typical use cases. So code-based ground motion simulation, where we just focus on, do simulations match response spectra relatively well? Regional risk applications with something similar, where we're focused just on the response spectra over the region. Are they site-specific for your particular location? And then that can be both for ground motion selection or for seismic hazard. So in conclusion, I've sort of touched on the link between the intended use and the necessary validation or acceptance criteria. The use case is really important because it allows us to focus on these features. Our simulations are not perfect, but that doesn't mean that we can't use them for certain different use cases as we slowly develop them. And those use cases will help accelerate the feedback loop that ultimately means that our advancement of those will proceed faster. And so we should base acceptance criteria not on trying to be nearly perfect, but simply doing better than what the conventional alternative is. That's certainly the clear message coming from engineering end users. And consider the development of federated databases of these simulated ground motions from heterogeneous groups, methods, regions to focus on intended use case as a simple metadata attribute. Here's just some references for people watching the video later, and thank you for your attention.